Richard Feynman once said, "What I cannot create, I do not understand." So comes the case with kinematics, and in this video, I'll try to not only give a breakdown of these equations, but try to build a geometric foundation around motion. If we look at the simplest example, we can plot out how velocity, or the speed, changes as time moves on. Let's look at an example. Say we're traveling for 4 seconds at 1 meter per second. How much distance have we covered under this time? Well, we know that velocity is how fast position is changing per unit time. And if we multiply that by how many unit times we have, we get the total distance traveled. Position is thus velocity multiplied by time. In this example, we would have traveled for 4 meters in total. But hold up. You might be asking, that's not true. What if velocity isn't constant? Well, that's a very good question, and let's go back to our graph again. Instead of traveling at 1 meter per second for the entire journey, let's say we decide to suddenly increase our velocity to 2 meters per second halfway through. To calculate the distance traveled, we'll have to break up the journey into 2 chunks. During the first half of the journey, we traveled for 2 seconds at 1 meter per second, for a total of 2 meters. For the second half, we traveled for 2 seconds at 2 meters per second, for a total of 4 meters. Summing it up, we covered a total distance of 6 meters. Notice how this is very similar to a bar graph, and we're just adding up the area of each individual bar. Now let's look at how we can expand this idea to more general concepts. If we change our speed 4 times, then we have to break our journey up into 4 parts, which is equivalent to finding the area of each of the 4 bars and adding it up. The same can be applied if we change speed 8 times, or 16, or 32, or 64. Notice that as we go on, the shape becomes closer and closer to a triangle. Instead of adding up the area of each individual bar, we can add up the area of the triangle, or the imagined triangle, and it will give us an accurate approximation. The more often velocity changes, the more accurate this approximation is. Therefore, if velocity is constantly changing, we can represent it as a triangle. To sum it up, position is the area under the velocity time graph. We will use this key concept to derive the kinematic equations. Let's look at some more properties of this graph. What is the slope? Remember from algebra that slope is equal to rise over run. The rise in this case is the velocity, and the run is the time. Velocity over time is equal to acceleration. This brings us to our second conclusion. The slope of a velocity time graph is acceleration. As a quick recap, acceleration describes how fast velocity changes, and velocity describes how fast position changes. Well, what is the final velocity of this graph? Well, if you look at it, the final velocity is just the slope multiplied by the time, the independent variable. Substitute in slope and you get acceleration times time. If you're confused about where that expression comes from, I'll explain it very shortly. Now, if the object we're looking at starting off the journey with a starting velocity, we'll have to shift our entire graph up a bit, because it doesn't just start at 0. It might start at 1 meter per second and then change from there, and add the starting velocity to our equation. This equation is analogous to the slope y-intercept equation of a line. Y equals mx plus b. Y is the final velocity in this case. M is the slope, or acceleration. X is the independent variable, or time. And b is the y-intercept, or the starting velocity in this case. We can represent each of these with a variable, and we have our first kinematic equation. To derive the second kinematic equation, let's solve for area. Recall that area is equal to the distance traveled, and the area under the graph is divided up into 2 shapes, a triangle and a rectangle. Let's find the area of each individually. The area of the rectangle is equal to the starting velocity multiplied by time. The area of the triangle is equal to half of the product of the width and the height. The width is the time and the height is the acceleration times time. Adding these up gives our total area. We can then reduce everything to their respective variables. Notice how in the second term there are two t's, so we can multiply them together to become t squared. After rearranging them, we get our second equation. The change in distance is equal to the starting velocity multiplied by the time plus half of the acceleration multiplied by the square of the time. The derivation of the third and final kinematic equation is a bit more counterintuitive. Recall that the acceleration is equal to the change in velocity over the change in time. Therefore, time is equal to the change in velocity over acceleration. Let us now substitute this expression in to the independent variable to get rid of time. Looking at the triangle, we can see that the height of the triangle is just the change in velocity, so we can substitute that in to get rid of the variable time again. Using the same method as the previous equation, we solve for area, which is equal to this. Take some time to look this over and proceed when you understand it. Now, we need some algebraic manipulation, so let's focus only on the equation. We see that both terms have a delta v over a, so we can factor that out. Expanding the delta v in the parentheses gives us this. And after expanding it, we can combine the terms and simplify. Now, we can expand the other delta v and then multiply the two together, giving us the final velocity squared minus the original velocity squared all over twice the acceleration. Remember, this is equal to the area under that graph, or the distance traveled. Expanding it out, and we can solve for final velocity, our third and final kinematic equation. I hope this video was helpful in understanding how the kinematic equations worked geometrically. Thank you and have a nice day.